Welcome back, everybody. Can you hear me well? Is the sound okay, guys? Okay, so welcome back, everybody, and hope you had a great weekend. So the topic this week is to try to get into the type of motion we can have with a gravitational force. But we're going to use the harmonic oscillator as a stepping stone, because that's an easier case, and it allows us to use what we had before. And we are going to look at the harmonic oscillator in 2 dimensions. And for specific values of the radius, which we choose as an initial radius, we are going to get circular motion. But we will also get elliptical motion with the harmonic oscillator. So we are going to dive into the whiteboard rather soon. And then I will be going a little bit back and forth between the whiteboard and us running codes. And the topics which I'm bringing up now are very relevant for exercises 2 and 3 in this coming homework. Then next week, we are not going to have any homework assignment. We're going to begin with the second midterm, and we're going to set aside 2 weeks for that. So you get plenty of time. And I actually haven't punched in the final score for the first midterm, and that's actually because I forgot to do so this weekend. So I hope you can forgive me for that, but it should come pretty soon. I'm slow with the grading. It's fun to make the exercises. I love reading your answers. The answers were fantastic, but grading is actually one of these kind of boring activities. Sorry. Okay, so let's get into the whiteboard and look at the equations which we derived last week and how we can use them to solve the harmonic oscillator, which is essentially exercise 2 and 3 in this coming homework. And you will need that one as a stepping stone towards setting up a code for the Earth-Sun system. So it's going to be pretty similar to that. The only thing which happens is that the force is going to change. So let's take a look at the equations which we set up last week and link these with the harmonic oscillator. Now let me just bring this up. So we should have the whiteboard up here. Now, what we did last week was to go through a series of technicalities. And I just wanted to bring up the equations so that we don't get lost and we actually do see the woods for the trees. And hopefully with many of these equations, we can catch many birds with just 1 stone. So today I started the day with lots of sayings. Let's see if I can continue along that way. Okay, so what we did last week was to define, since we just were looking at 2 objects, so this is a topic of 2 body forces, we defined the center of mass position, which is a weighted average of the positions of 2 objects, and divided with a total mass, where the total mass is simply m1 plus m2 here. And then we define the relative motion or the relative position, which is simply r1 minus r2. And then came a series of technicality which we went through. And let me just repeat them for you, just listing the final results. So one thing which we do is to choose the central mass frame, COM is center of mass. And in that case, we simply choose r equal to 0. And that led to dp dt, the momentum, the time derivative of that one, equal to 0. And this is something which takes place when we have forces of the central type and energy conserving forces as well. And we are going to look at the force which looks like this, which comes from, for instance, the gravitational potential. So what we saw then is that the linear momentum is conserved when a time derivative, which is equal to the force, is equal to 0. And when we have internal forces only, this is actually the case. And just to quickly remind you of P, that is the same as M times d of r dt, which means again that since P is a constant of the motion it means also that the central mass velocity is a constant of the motion. Next, what we saw is that angular momentum is conserved. So if we take L, and when I write this R here, that stands for the relative momentum, no, the relative position, and P is the relative momentum. Then what we could show is that dl dt is also a conserved quantity. So L is conserved, it's a constant. And that allowed us to reduce the problem to a two-dimensional problem only. So when L is conserved, since it's spanned by R and P, it means that R and P can be defined to lay in a plane, and L is perpendicular to the plane. And since it's conserved, nothing happens if we define the direction of L to be the z-axis. So that means that we could reduce the problem to a two-dimensional one, 2dim. And in that case, we took the relative position and rewrote that in terms of the unit vectors. So we have a y times j, the unit vector in the y direction, and r goes from 0 to plus infinity. R is given by x squared. So if you don't see an arrow, this is always an absolute value. So when I don't put arrow, in case I've the cases when it happens that I may forget to put an arrow, but normally if you don't see an arrow, this is just a scalar. And in our case, R is the absolute value without the vector sign. And then we have that the angle phi is defined between 0 and 2 pi. So we are just in two dimensions. And remember here that x is defined actually from minus infinity to plus infinity. And the same with y here. It's defined in the same domain. So we made this change of variables to r and the angle phi, which is going to simplify the equations for us. Then what we needed and what we did was to find the equations in terms of the radial velocity and the radial acceleration. We also had the angular velocity. So these quantities here have their names. So this is the radial velocity. So instead of having the velocity in the x direction and the velocity in the y direction, we have the radial velocity. And this other quantity which you see here is just the angular velocity. So these are names which we're going to use again and again. So instead of x and y velocities, we have radial and angular velocities. Now, another quantity which we derived last time was the kinetic energy in this new basis. So in two dimensions, the kinetic energy, K, so let's just remind you that when I use the letter K, uppercase letter, K, that's the kinetic energy. K is in two dimensions. You can write it out in terms of the velocity in the x direction plus the velocity in the y direction. Or alternatively, if you have the new coordinates, so in our case, this is multiplied with mu. Alternatively, mu is the reduced mass. So let me just remind you of that definition as well. So this has the radial velocity squared, but then it contains the radius squared multiplied with the angular velocity squared. So this is one of these transformations we made last week. And we have m1, m2 divided by m. So last week was a kind of technical week where we needed to go through several of these small technicalities. Then the other thing which we derived last week was actually the differential equations which we need to solve. So we had a differential equation for the angular velocity. And since angular momentum is conserved, this is equal to angular momentum divided by r squared. And L is conserved, and r is just the radius. So there is a dependence between the angular velocity and the radius. And this is something which when we come to the gravitational force, we are going to find an expression of the radius in terms of the angular velocity, no, not the angular velocity, but the angle phi. So we're going to use the chain rule and some tricks in addition to find the solution to the differential equation. But the differential equation which we ended up with for the radial degrees of freedom, so this is a second derivative. This is something which we can then write as the radial acceleration. This was given by a force, which we have not yet specified, plus this angular momentum term, L divided by mu over r cubed. And we call this for an effective force, where this angular momentum term actually comes from the kinetic energy. So when we had the expression for the kinetic energy, what we did was to go back to the expression which you see here, this one. And since we know that the angular velocity is proportional to the angular momentum divided by the radius squared, then we isolated terms which depend on the radius only. So when we look at the total energy, you could now say that why should you mix a term from the kinetic energy into the potential energy? Now, the reason for that is that you isolate one term which depends simply on the radial velocity and two terms which contain only the dependence on the radius. And then you can define an effective potential. And that's going to be very useful when we are going to analyze the type of motion. And you will see that when we come to the harmonic oscillator today. So the reason why we did this is when we now look at the energy. So let's just bring this up here. So the energy E is equal to potential energy plus kinetic energy. And in our case, we are just going to write this out now in terms of the kinetic energy. So we have an m times mu, and then we have this r dot plus this r squared times phi squared multiplied. Now we add the potential, and we haven't specified the potential yet. Then what we do now is that we simply say that we isolate the radial motion only. So we have the radial velocity. So we would have a 1/2 of mu of r dot squared. And then we have an additional term, which we call for an effective potential. And this effective potential, since we now have this term coming from here, the only thing we do now is simply to plug in the fact that angular momentum is conserved. So we go back to the equation we have for angular momentum. And I think I put it up here. So we're going to take this expression here and plug that one in for the angular velocity. So that means that this potential which we have, this V effective of R, is now going to be something which we define as the original potential plus this angular momentum dependent term, which goes like L divided by 2 times mu times r squared. So this is going to be the effective potential. And we see now that this effective force, the effective force is going to be the derivative of dV of d of r, effective. And if I plug that in, we are going to have minus dV, the original potential, which could be the gravitational potential. And then I have plus a term which goes like L squared, the factor of 2 disappears, and I have mu divided by r cubed. And this term, the first one, is normally the term which we would link with, let's say, the gravitational force. And then we have a term which depends only on the radial degrees of freedom. And that's why we lump this one together with the potential. So we have one term which defines the kinetic energy in terms of the radial velocity. And then we have one term which actually comes from the kinetic energy and the angular velocity, but it depends only, due to the fact that angular momentum is conserved, it depends only on r squared. And then we just lump it together with a potential, and we call this one effective potential. This is something you're going to see again and again in physics. Now, in the for the harmonic oscillator case, if you stay with Cartesian coordinates, as we will see, x squared and y squared, then you would have to make a plot in terms of X and Y. So what happens when we move to polar coordinates is that there is no angle dependence, and then we can plot the potential as a function of the radius only. And that gives us a, one way to analyze the equations of motion, which sometimes is a little bit easier. So if you now look at the plot, which we made last time, if we now collect the total energy here, you can now think of this as one which just has the radial velocity. And then we have a radius dependence only here, since angular momentum is conserved. So we have now, if we now make a plot of the energy, if we now take a potential, suppose now that V of R is given by some gamma, some constant divided by R, then when we plot this V effective, it's going to look something like this. So this is going to be V effective. And this reminds us of what we saw in previous exercises, like when we looked at the first midterm, when we had this particle which was confined to move in, let's say, a harmonic oscillator type potential, or this potential with a linear term, so the particle could never escape. This is a type of potential which we see again and again in many, many physics applications. But keep in mind now that what we have done is to plot an effective potential, which then contains a term here. So if we ring in this term here, this is normally called a centrifugal barrier. And it depends actually on the angular velocity. So let's now go into the first example, and this serves as a stepping stone towards the equations with a gravitational force. And this is actually a simpler set of equations. So let's do the two-dimensional harmonic oscillator in order to illustrate what happens. Harmonic oscillator. This is actually one of these nice cases in physics where we can separate degrees of freedom in Cartesian coordinates. And that often makes the solution of the problem much, much easier. So what we have now is a potential which is given by 1/2 of k times r squared. And we could actually rewrite this one in terms of x and y, because it's equal to 1/2 of k, the constant, the spring constant, x squared plus y squared. So that's the harmonic oscillator in 2 dimensions. So whether we use r or x and y is going to actually give us equations which, and as you will see, they are easier to solve in the Cartesian coordinate system. If we now make the transformation from x and y to r and phi, we can actually rewrite the total energy of the system in terms of 1/2. We would have m. Let's use the reduced mass here so that we don't make a confusion from now on. So I'm just going to use the reduced mass. So I would have x, the velocity in the x direction, and the velocity in the y direction, plus 1/2 of k, and then I have x squared plus y squared. And when I rewrite this in polar coordinates, it's going to be 1/2 times mu times r, the radial velocity squared, plus this term r squared of phi, the angular velocity, plus 1/2 times k times r. So this is the energy of the system. And that means that we can define an effective potential now in the same way as we did for the general case. And this effective potential becomes now 1/2 times mu of r squared of phi dot. And we can show that in this case as well, so this should be an r squared. We can show in this case as well that angular momentum is conserved. And this gives us a effective potential, which is going to be given by L divided by mu times r squared plus 1/2 times k multiplied with r squared. Now, this equation here is actually easy to solve for the x and y degrees of freedom. I'm also going to bring up the equation of motion. So this is the acceleration in the radial direction. And that's going to be given by the standard harmonic oscillator force, k times r, plus this term, which goes like L squared divided by mu over r cubed. So that equation there is an equation we want to solve. And actually that equation is easier to solve in Cartesian coordinates. So if we move the polar coordinates, this is a kind of clumsy way of trying to solve the same type of equation of motion. Because in Cartesian coordinates, we have a cosine and sine solution. Now, if we now make a plot of the potential here, there are some interesting things which we can extract from it. So let's plot this effective potential here. And we want this V of effective minimum. And this is now given, as I said, of k times r squared plus this L squared divided by 2 times mu of r squared. So now I'm going to give you a small exercise. Find this minimum radius at the minimum of the potential. So we just take a small break, and then we ask ourselves, what is our min? So what kind of thing should I do then to find the R min here? What kind of mathematical operation should I do on this effective potential to find R min? It's the same thing which you did in the midterm and earlier exercises. So how do I find R min here? Take the derivative, right? Okay, so let's take the derivative and let's take 5 minutes on that and then see where we get and see if we can find R min. So we take the derivative of that function, v of f, and then set that one to 0. And that should allow us to find the minimum. So what we want now is dvf, this potential, and d of r, and at r equal to the minimum value, and we want that one equal to 0. So that's going to allow us to find the minimum value here. So let's just take 5 minutes and see if we can get the value. Okay. So does that agree with what you guys got? Good. Yeah. So now comes the next question. Because when we took the derivative of this effective potential, this is essentially what we did to find the minimum. So to get the minimum at this point, we took the derivative and put that to 0. Now, what is the derivative of the effective potential? That's the effective force. So let's bring that back. That's a good point. So this becomes important for us because this is going to tell us something of the type of motion which we now can expect. So let me bring back the equations. So we know that this effective force, dV of E of F, which we now put equal to 0 at R, equal to R min. And if I put 0 minus here, it doesn't matter because it's 0. This is the same as the effective force. And this effective force is nothing but A times R, which is the radial acceleration. And we actually put that one to 0. Now, there's another equation which we also need to think of, and that's the equation for d phi dt, which is equal to L divided by mu divided by R squared. Now, if you now are at this minimum, what does this actually mean? What kind of velocity do you have at this minimum point? Let's say, yeah, but what would you say about the velocity in the radial direction? It's constant. Perfect. So what we have now, you see that we can fix the angular momentum. That will change the angular velocity. But now at this R min, so that means that we are plugging in R min here. So just a constant. L is a constant. The reduced mass is a constant. So everything here is a constant. That means that the angular velocity is also constant. And the velocity, the radial velocity, is a constant because we have 0 acceleration. So when both these two things kick in, that means constant angle. No, not constant angle, but constant angular velocity. And a constant radial velocity, that means that we have circular motion. That's the definition of circular motion. So when we look at this bottom point here, and we make a plot here. So let's now make a plot in the XY direction. So this is X and Y. So we could now think of R min being here. So this is our R min. And then we would have minus R min here. Remember that X goes from plus infinity to minus infinity. So you can have a place where X is equal to R min, or X squared plus Y squared is equal to R min. But R min is a constant. And in our case now, if we now attempt at drawing a circle, and we put the angle here, phi, what we have here is that d phi dt is a constant because it's given by this R min. And if we now just bring it down here, so this is equal to L divided by mu and R min squared. So we say that the angular velocity is a constant. So this means that this object, when it goes in the XY plane, it goes in a circular orbit all the time. So I know this doesn't look very much like a circle. Just imagine it is a circle, right? Be kind to me. My drawing skills are pretty limited. Anyway, this kind of system has also can also exhibit when we now move away from this minimum, as we will see on Wednesday. This system can also have elliptical orbits. So we are not limited to have a circular orbit, but what we've seen now from the equation of motion here, if we go back, we can now single in here a circular motion. It has a given energy. It doesn't have a zero potential energy. It doesn't have zero kinetic energy, but it has constant angular velocity here. Okay, so we can now, if we look at this system here, we could now take a look at the solution in the X and Y, for the X and Y degrees of freedom. So let's now go back to Cartesian coordinates. And try to link the two, because that's something which you will need to do in homework 2 and 3. Because now you've seen that for the angle phi, there is no point in solving a differential equation as long as you know the radius as a function of time. So that means that we can focus only on the solution of the radius. So in that sense, we have reduced a two-dimensional problem to a one-dimensional problem for the radial degrees of freedom. So that means that you, instead of solving a two-dimensional problem, you just need to solve a one-dimensional problem. And when you have R, you can then go back and put that one for the equation for phi, and then you will find the angle. So this is something which simplifies somewhat the solution, but for this specific case with the harmonic oscillator, what we know now is that in that specific case, we get an equation which goes like mu times d of x dt, and that's given by minus k times x. And then we have a similar equation for y. So the two equations separate, and this is one of the nice features of the harmonic oscillator, which means that we will get a solution of the type x of t given by some constant a of cosine, and then we define this frequency again, and we have a b, and we've seen this solution many times now, where this omega is given by the square root of k divided by n. And then we have a similar solution for y of t, which is now given by c times cosine of omega times t plus d times sine of omega of t. So now we can start thinking of choosing initial conditions. So if we now go back to the radial type of equations, and we stay with circular motion. So at r min, what we had is that we have that the radial acceleration, a of r, is equal to 0. If we look at the initial conditions, which we could choose now, initial conditions, because we need them to find these constants, a, b, and c, and d. So if we make this plot again of the circle, so this is my second attempt to make a circle today, and most likely I'm going to fail again. So we have the r min. So we could think of an initial vector, r0 of t, which is now given by r min. So we have only the value in the x direction. And then we could now think of an initial velocity, which is perpendicular to that one. So we could think of a v0 that direction, or a v0 in this other direction. So this is the initial condition which we could choose. So we would then choose an r0 at time t0, which we just label as r0. And that is going to be given by some x0 times I plus n of y0 times j. And in our case, we choose y0 to be 0 and x0 to simply be this r min. So that's a choice which we can make now, and which often simplifies the numerics. And then what we can show, if we now use the what is called the centripetal acceleration, and I think you've seen something like this in physics 181, centripetal acceleration. So let me just remind you of the definition here. And that's actually defined in terms of AC, centripetal, is now given by this radial. And this is now the same as our velocity divided by r min. So I can plug in this r min, which we found previously. And you will see now that when I plug in this r min, this is actually going to be equal to the force, which is, in our case, the same as K. And now we are taking the absolute values, K of r min, divided by the mass, mu, like this. And K divided by mu gives us omega squared. So that means that when we now perform the calculations here, using that omega squared is the same as K divided by mu. What we see then is that this velocity v squared is the same as this omega squared times this r min quantity which we have. Which means that the velocity is something which we can fix to omega times r min here by using the centripetal acceleration. We can then define the initial velocity. So v0 as a vector, which is v at time t0. This is now equal to a v0x multiplied with the unit vector in the x direction plus v0y in the j direction. And in this specific case, we choose that one to be perpendicular to the x direction. So we could now choose v0 equal to an 0 times I plus this omega times r min times j here. And this is the same as v0y. So this could be a choice of initial conditions. And then we can go back to the solution in the x of t and y of t, and we can find the coefficients a, b, c, and d. So remember now that we have an infinity of solutions, and this infinity of solution is something you nail down when you have decided the coefficients a, b, c, and d, and they are defined by the initial conditions only. And now we have set up a set of initial conditions for this type of motion. So if we do that, we can now go back to the differential equation and the solution to that one. So we have an x here, which is given by this equation here. So if I put t equal to 0, obviously this term disappears. And then that means that this a has to be equal to r min when I put t equal to 0. And then if I take the derivative, I also know that the derivative of the x gives the velocity in the x direction. And the velocity in the x direction at t equals 0 is equal to 0. So let's see what we get when we plug in these equations here. So what we have now is that x of 0 is now obviously equal to a times cosine of 0 plus sine of 0, which is obviously 0, sine of 0. And this is the same as r min, because we chose the initial condition in the x and y direction to be so that x is 0 is r min and y0 is put to 0. So this is just reflected in the graph which we have here. So that means that a is equal to this r min. What we also know is that v0 in the x direction is something which we put to 0. And that's the derivative of this quantity. So that should be equal to minus a times omega 0 multiplied with sine of omega 0 times t0. And then I have plus b times omega 0 multiplied with cosine of omega 0 of t0. So t0 is 0. So that means then, since we have defined a value for a, we know that this quantity here has to be 0. And from this, it follows simply that this quantity b has to be equal to 0. And then we have the solution x of t, which is given by r min, multiplied with cosine, and then we have this omega times t. So the next thing we need to do now is to do the same thing for y. And we know that y of 0 is put to 0. So that's going to decide the coefficient c, which is going to be equal to 0. And then I use the velocity in the y direction to find the coefficient d. So when we do that algebra, and I'm just going to leave that as a small exercise to you, what you will find then is that y of t, or rather, we are going to find for y of t, we are going to have the constant d, which is going to be given by r min, but now it's multiplied with sine of omega times t. So for the harmonic oscillator, everything we did now in polar coordinates is an overkill. It's actually simpler to solve the equations in Cartesian coordinates. And that's because the potential is separable in x and y. It goes like x squared and y squared. When you have something which goes like 1 divided by r, that's already a flag that tells you that most likely my differential equations in x, y, and z are not going to be separable. And that's why we're going to go through this trick with the changes to polar coordinates. And then you will see that we can actually find the analytical solution for the gravitational two-body problem. But the thing I wanted to show you now is how we actually can encode the harmonic oscillator, because that's related to the first two exercises 2 and 3 in this homework assignment. So let's take a look at that. And as I said, this is a kind of stepping stone towards the gravitational force, which is obviously the more interesting case. But the harmonic oscillator with this kind of effective potential here is also going to give us an elliptic motion. If we place ourselves here and put the velocity equal to 0 there, then it's going to oscillate back and forth, and we're going to get a elliptical motion, which is still bounded. So you're going to rotate around the center. Now, if you look at the harmonic oscillator potential, can this object escape the potential? So could you get something like a hyperbolic or parabolic orbit? What is your feeling with the harmonic oscillator? If you think of the way it looks like, it goes to infinity, right? So it has an infinitely large potential, and you will always be trapped in the potential. So that means that the harmonic oscillator can only exhibit elliptical motion and circular motion at the bottom. So that means that the motion for the harmonic oscillator will always be bounded. So if somebody gives you harmonic oscillator potential, you can infer immediately that the motion is going to be bounded. That means that an object which rotates around something can never escape from the mass center. So it's like the Earth-Sun case, where the Earth does not escape from orbiting around the Sun, which is luckily for us, actually. It's a fortunate situation. But let's go back to the numerics a little bit and see what kind of results we would get and how we can program this, because we can actually program this in Cartesian coordinates, or we could choose to use polar coordinates. I mean, that's very much up to you, but you have to be careful then with the way you set up the initial conditions and also the way you're going to set up the initial conditions. So in this specific case, I'm just plotting this as a function of the polar radius, r. And you see in this case here, it's going to be a potential when we zoom it in at this minimum here. It's going to, with the parameter I've chosen for, I always, as you probably notice now, I'm pretty lazy with parameter choices. I put all these physical parameters equal to 1. That makes life easy when I'm going to plot results. Nothing wrong with that. And you see this is a typical effective potential, which we discussed in the on the whiteboard. And this will be the minimum position here. When you now solve it in 2 dimensions or in 1 dimension, if you solve it in 2 dimensions, like in this case here with the Cartesian coordinates, you see now that I have to define a velocity with the two variables. So this is x and y, the x and y direction of the velocity, and this is the x and y direction for a given number of integration points over time. I'm still defining omega squared, omega 0. I define the angular momentum to be 1, just for the sake of simplicity. And here, I'm putting in this result for the minimum. So what I've done now is actually to place myself at the minimum position by just choosing the results from the analytical calculation, which we did just a few moments ago. And when I solve this in Cartesian coordinates, then I have to be a little bit careful, as you can see. So I'm putting x0 equal to r min, as we discussed. And I put vy0 to the square root of omega times r min. And then I have my v0 in the x direction equal to 0. So now I have to solve an equation, and I'm using this compact notation with Python, where I'm actually defining a matrix where the rows refer to the time and the columns refer to the x and the y axis. And this gives us, again, a kind of compact equations. So the r, which you see here, this is now simply my acceleration, is nothing but r times omega squared. So this is a plane harmonic oscillator, right? Now, in this case, when I solve it for x and y, there is no effective potential. So just keep that in mind. Because the effective potential with this centrifugal force, that pops up only when you make the transformation to polar coordinates or to spherical coordinates. But just keep that in mind, because it's easy to make an error, because now we depend only on x and y. So r, which you see here, is just x squared plus y squared and square root of that. And then what we are going to get then when we solve the equation, so here I just took my favorite method for this kind of energy conserving problem, the velocity-Valère method. And I'm going to plot now the results. And you can see now radius. And you see this one is, it actually has a small oscillation. So it oscillates a little bit, but this oscillates around 1, where I have the minimum. And it has an oscillation of 10 to the minus 7. And that's simply due to numerical inaccuracy. Now, there's one thing you will notice when you solve things numerically. If you go to higher dimensions, you can actually, since you have more degrees of freedom, you will often get a numerical solution which has a larger error than when you solve it in one dimension. And you will see that when you now solve it for only polar coordinates. But this is something you can amend clearly if you now take, so this is a radius squared, and this is the x position. Remember also that these positions, x and y, so this is the radius, and that should be the radius. What should it be now, actually? This is the radius squared. What should you get when you're at the minimum? So x and y, you can see they oscillate, right? Because these are sine and cosine solutions. But what should I get for the radius? It should be 1 exactly. It should be as flat, as I used to say, as the Netherlands seen from the sea. So if I increase or decrease my step size, and suppose I make this smaller and rerun it, that takes a little bit more time, but you will see a much smaller error now. So the envelope is 10 to the minus 11th. So this is now the error I'm making. And r is actually x squared plus y squared. And since I have a cosine and a sine, these will oscillate. And a small inaccuracy is going to make this radio oscillate around 10 to the minus 11. On Wednesday, we are going to, if you scroll down the codes here, you will see the similar code for the polar coordinates only. And then the radius is just going to be dead flat. So that's a typical thing you will see often when you solve things in higher dimensions. But the physics should be exactly the same, except that now we suffer a small numerical error, which is 10 to the minus 11th. So on Wednesday, we are going to switch to the gravitational force, and then it's going to become more fun here, because then we can have more types of motion. Okay, guys, great pleasure seeing you all again here. Have a good one, hey? So